quantum experiments are computing things that a classical computer can't compute. So they're somehow able to compute very quickly things that are very difficult to do classically. And that turned out to be correct. And in fact, the example I want to show you is one of these amazing things that, in fact, if you could build a quantum computer that's using quantum physics, then in fact you can solve this search problem not in time x, but in time square root of x. So somehow, even though the computer doesn't know anything about the function f, it's treating it as a black box, nevertheless it's able to find a point when the function is 1 in time square root of x. I'm not going to explain this here, but at the end of the class we're going to have an advanced topics lecture, and if you'd like me to explain how this algorithm works, I can explain it in that advanced topics lecture. It's actually quite interesting, and in fact quantum computers have quite an impact on crypto, and again, as I said, I can explain this in the very last lecture. Alright, so what does this have to do with breaking block ciphers? So far it's just a generic search problem. Well, actually I guess I should say before I show you the application, I should mention that, well, you might be wondering, well, can someone build a quantum computer? And this is still completely unknown. But at this point, nobody really knows if we can build large enough quantum computers to actually take advantage of this beautiful algorithm due to Grover. All right, so what does this have to do with block ciphers? Well, so suppose I give you a message and a ciphertext pair. Just one or just a few. We can define a function as follows. It's a function on k. It's a function on the key space. And the function will basically output 1 if it so happens that the encryption of M with K maps to C, and it will output 0 otherwise. Now we argue that basically this is exactly the type of function that's 1 at one point in the key space, and that's it. So by Grover's algorithm, we can actually find the secret key in time square root of K. So what does that mean? For DES, this would totally destroy DES. This would say that in time 2 to the 28, you can find a key. 2 to the 28 is about 200 million, so 200 million steps, which is, this takes a millisecond on a modern computer. This would totally destroy DES. But even AES with 128-bit keys, you would be able to find the secret key in time roughly 2 to the 64. And 2 to the 64 is these days considered insecure. That's within the realm of exhaustive search. And so basically, if somebody was able to build a quantum computer, we would then say that AES 128 is no longer secure. Instead, if somebody, if tomorrow you open up the newspaper and you read an article that says, so-and-so built a quantum computer, the consequence of all that is that you should immediately move to block ciphers that use 256 bits, because then the running time of Grover's algorithm is 2 to the 128, which is more time than we consider feasible. And basically, there are example ciphers with 256 bits, for example, AES 256. This is one of the reasons why AES was designed with 256 bits in mind, but to be honest, this is not the only reason. There are other reasons why you wanted to have larger key sizes. Okay, so this is, as I said, just a taste of the different attacks on block ciphers, and I'm going to leave it at that. If we decide on quantum for the last topic of the course, then we'll cover that in the very last lecture. Over the years, it became clear that DES and triple DES are simply not designed for modern hardware and are too slow. As a result, NIST started a new process to standardize on a new block cipher called the Advanced Encryption Standard, or AES for short. NIST started this effort in 1997 when it requested proposals for a new block cipher. It received 15 submissions a year later, and finally in the year 2000 it adopted the cipher called Rindel as the Advanced Encryption Standard. This was a cipher designed in Belgium, and we already said that its block size is 128 bits, and it's got 3 possible key sizes, 128 bits, 192, and 256. And now the assumption is that the larger the key size is, the more secure the block cipher is as a pseudo-random permutation. But because it also has more rounds involved in its operation, the slower the cipher becomes. So the larger the key, supposedly the more secure the cipher, but also the slower it becomes. So for example, AES 128 is the fastest of these ciphers, and AES 256 is the slowest. Now AES is built as what's called a substitution permutation network. It's not a Feistel network. Remember that in a Feistel network, half the bits were unchanged from round to round. In a substitution permutation network, all the bits are changed in every round, and the network works as follows. So here we have the first round of the substitution permutation network, where the first thing we do is we XOR the current state with the round key, in this case the first round key. Then we go through a substitution layer where blocks of state are replaced with other blocks based on what the substitution table says. And then we go through a permutation layer where bits are permuted and shuffled around. And then we do this again. We XOR with the next round key, we go through a substitution phase, and we permute the bits around. And so on and so on and so forth until we reach the final round where we XOR with the very last round key, and then out comes the output. Now, an important point about this design is that, in fact, because of how it's built, every step in this network needs to be reversible so that the whole thing is reversible. And so the way we would decrypt essentially is we would take the output and simply apply each step of the network in reverse order. So we start with a permutation step, and we have to make sure that step is reversible. Then we look at the substitution layer, and we have to make sure this step is reversible. And this is very different from DES. In DES, if you remember, the substitution tables were not reversible at all. In fact, they mapped 6 bits to 4 bits, whereas here, everything has to be reversible, otherwise it would be impossible to decrypt. And of course, the XOR with the round key is reversible as well. Okay, so inversion of a substitution permutation network is simply done by applying all the steps in the reverse order. So now that we understand the generic construction, let's look at the specifics of AES. So AES operates on a 128-bit block, which is 16 bytes. So what we do with AES is we write those 16 bytes as a 4x4 matrix. Each cell in the matrix contains 1 byte. And then we start with the first round. So we XOR with the first round key. And then we apply a certain function that includes substitutions and permutations and other operations on the state. And again, these 3 functions that are applied here have to be invertible so that, in fact, the cipher can be decrypted. And then we XOR with the next round key, and we do that again. Again, we apply the round function and XOR with the round key, and we do that again and again and again. We do it 10 times, although interestingly, in the last round, the mixed column step is actually missing. And then finally, we XOR with the last round key, and out comes the output. Again, at every phase here, we always keep this 4x4 array, and so the output is also 4x4, which is 16 bytes, which is 128 bits. Now, the round keys themselves, of course, come from a 16-byte AES key using key expansion. So the key expansion maps us from a 16 bytes AES key into 11 keys, each one being 16 bytes. So these keys themselves are also a 4x4 array that's XORed into the current state. Okay, so that's the schematic of how AES works, and the only thing that's left to do is specify these 3 functions, byte sub, shift row, and mixed column. And those are fairly easy to explain. So I'm just going to give you the high-level description of what they are, and those interested in the details can look it up online. So the way byte substitution works is literally it's one S box containing 256 bytes, and essentially what it does is it applies the S box to every byte in the current state. So let me explain what I mean by that. So the current state is going to be this 4x4 table. So here we have the 4x4 table, and to each element in this table we apply the S box. So let's call it the A table, and then what we do is essentially for all 4x4 entries, essentially the next step, Aij, becomes the current step evaluated at the lookup table. So we use the current cell as an entry, as an index into the lookup table, and then the value of the lookup table is what's output. Okay, so that's the first step. The next step that happens is a shift row step, which is basically just a permutation. So essentially, we kind of do a cyclic shift on each one of the rows. So you can see the second row is cyclically shifted by 1 position, the third row is cyclically shifted by 2 positions, and the third row is cyclically shifted by 3 positions. And the last thing we do is mixed columns, where literally we apply a linear transformation to each one of these columns. So there's a certain matrix that multiplies each one of these columns, and it becomes the next column. So this linear transformation is applied independently to each one of the columns. Now, I should point out that so far